Hi, my name is Hugo Tremblay. This is a short overview of a work I did with my colleague Sylvain Allais, entitled A Generic Explainability Framework for Function Circuits. The idea is to present a theoretical model for data lineage using functions, graphs, and an abstract structure called a designator, in order to gain information about the provenance of some result of a computation. Our basic processing unit is a function, which can have any number of inputs and outputs. We can consider functions as essentially black boxes with input pins and output pins. Those functions can be composed to form a circuit, which is a graph where the vertices are the functions and where output pins are linked to input pins. Of course, some input pins have no ingoing arcs and some output pins have no outgoing arcs. They correspond respectively to the input pins of the circuit and the output pins of the circuit. A circuit itself can be considered a function with its own input pin and output pins. Most provenance models implicitly involve the concept of being part of something. And it's rather straightforward to define it in the relational world. For instance, if we have a relation, which is a set of elements, and we want to define being a part of that relation, we simply use the standard subset operator. But what if the universe of discourse is richer or more complex and not only made of sets? How can we define the part of relationship? Our proposed model is based on an abstract topology of objects. Basically, we have a list of objects with a partial order on the objects, such that scalars have no parts but themselves. A part of a set is a subset or a single element. A part of a string is a substring, and so on and so forth. And based on that, we can define a designator simply by a function that takes as an input an object and returns a part of this object. For instance, the nth element of a list is a designator. We have some designators that returns contents of some file. Designators can return outputs or inputs of functions, so on and so forth. And what's interesting is because designators are themselves functions, they can be composed as usual. For instance, this compose designator operator is the first 5 characters of the third item of the second argument of a function. Using these definitions, we can define a designation graph, which is an n or tree that can provide information about inputs and outputs of functions. So this graph can be defined for a given circuit and given input of that circuit. For example, take this circuit, which takes as an argument a file and splits it into lines. Then for each line, we apply the following sub-circuit, which take the line, splits it on commas, take the second argument, and convert it into a number. Then we take a sliding window of size 3 and compute the average of the numbers in the sliding window. Then for each average, we compute another sub-circuit which checks if the sum is greater than 3. And then finally, if all averages are greater than 3, then the circuit returns true, otherwise it returns false. So in this example, for the following file, we can construct this designation graph, which provides interesting informations. First, the OR node here suggests that there's 3 possible explanations for the fact that these circuits evaluate to false, since there is 3 outgoing arcs to this node. Those 3 explanations, of course, corresponds to 3 problematic sliding windows. The first one being 18 to minus 80. the second one being 2 minus 87, and the third one being minus 87 and 1. And also, the graph suggests that some lines are more important by being involved in all possible explanations. This is the case of this entry here, which correspond, of course, to the line containing the minus 80, which is the main explanation because why the computation returns false. And this kind of multiple alternate explanations would not be possible in a structure that does not support it. Of course, there's some further work to be done here. We would like to propose formal definitions for a model and test it on several frameworks. Thank you for your attention.